Okay, so we're now going to look at the second part of the lecture, which is the relational algebra. So we've looked at the first part, and what did we learn in the first part? What did we learn in the first part? Integrity. We learned some kind of rules. We learned about the primary keys, which are important to the relational model. The mathematical basis, including all these things on set theory and relations. And like the constraints, like what integrity constraints does the relational model have? 3. The first one is?
Structural.
Yeah, the structure is the kind of the timers and so on. But then we move on to the constraints. There are 3 main constraints. Domain integrity.
Uniqueness.
Sorry?
Uniqueness.
Yes, well, that's part of defining a primary key, but it's not one of the main constraints of the relational model. But it does come into it in the form of entity integrity. Because in entity integrity, we have to guarantee uniqueness and we have to guarantee that no part of the primary key is null. Okay, so that's entity integrity. Then there's the domain integrity that somebody mentioned, and then finally there is what? Referential integrity, which means that when you have a candidate key, the reference of that candidate key, a foreign key, it has to have a valid reference to another candidate key, possibly a primary key, or be wholly null. Okay? So those are the things that we have looked at. Now we need to look at relational algebra, because it's a way in which we can manipulate data in the relational model. We need to understand when it's used, and we need to be able to formulate simple queries in relational algebra. And for that, you need to read Connolly and Beck chapter 5. There used to be a software in the labs called WinLib, which might still be there, which allows you to practice relational algebra a little bit. We don't do it anymore, but if you did want to go on to that, ask me, and I will give you something to do on it. So why do we actually bother to study relational algebra? Well, it is the basis for other query languages. So relational algebra was what they defined first before they moved on to define query languages such as SQL. So understanding relational algebra helps you to understand how SQL works. It defines some basic operations on relation, and it's very close to mathematical kind of like thinking, so it helps you to understand the mathematical thinking behind the relational model. And out of that come more user-friendly query languages such as SQL. Also, it is an intermediary layer in the execution of a query. So when we write a query in SQL or through an applications program, whether we do it through applications program or interactively, that gets translated by the DBMS into relational algebra, because a lot of the query processing is done by looking at the relational algebra. So it is important that we understand relational algebra from that point of view, because when we come to query processing, we'll be looking at it from the relational algebra point of view. And once that happens, then the query optimizer decides how the query is going to be executed, and there is the file access, the pages that are required for the particular query are brought back from secondary storage to main memory, etc. So we begin to count how many disk accesses we do. So in terms of query planning and optimization, it's very important to understand relational algebra. And apart from that, I tend to ask questions of it in the exam. So even if you didn't think it was very important, you still have to learn it, because otherwise you might find yourself struggling in the exam. So it is a procedural language, and that means that we tell the database management system how to build a relation from other relations. When we go to non-procedural queries like SQL, we tell the system what we want, but know how it is going to get it. But relational algebra is procedural. It tells the system how it's going to compose a new relation out of other relations. So it is what we call a procedural language. And it always operates on a set of tuples, which is a relation, and the intermediary and final results are also a relation. Because of that, it has the property of closure. And that means that we can stack relational algebra operations in parentheses, like we do with maths, because the intermediary results will be a relation. So I can stack operations together using brackets, because everything will be a relation, and then I can operate again on it. So it's got this property of closure. The operands are results are relations, and I can nest the operations of relational algebra in using brackets. So that is an important property. So the first of the relational algebra operations that I'm going to look at is the restrict operation, and that allows me to select a set of tuples which satisfy a specific predicate. So I define my predicate, and then the relational algebra operation will select those tuples that satisfy the predicate. So it's a horizontal selection because I'm selecting tuples. Okay, I'm selecting records or objects in the database, like that. So it's horizontal. So if I have something like a supplier table where I have a number of suppliers with their name, the number, the status, and the city, I can define a relational algebra operation that says select, and that's the letter for select, city equal London. This is my predicate. So my predicate is telling me select the tuples where the city is equal to London from the relation supplier. And this is going to return another relation because it's got closure, but the only tuples that will be there will be those where the city is equal to London. So S1 Smith London will be included. S2 Jones Paris will not be included. Blake will not be included. Clark will be included. Okay? And Adams will not be included. So it's quite simple. It's called restrict to select, and it restricts particular, it selects particular tuples according to a predicate. Do we all understand that? Yes?
Is it valid to use, if you wanted to select two cities,
Yes?
put like brackets? Or
Yeah, you could say city equals London or city equals Paris.
you use or, not comma?
Yeah, you do or, because you can use like the logical operators within it. So you what you will do is build a predicate using the logical operators that gives you the selection that you want. So then we have projection. Projection is actually a vertical selection. So what we do with projection is we select particular attributes. There is no horizontal selection here. What we're saying is we want to return particular attributes. So, and remember that, well, we will see this in a minute. So we're looking at vertical selection, and what I have here is, for the original relation, I have its number, its name, status, and city. So projection, which is this symbol here, I want to project two particular attributes, status and city. I could project as many as I like from supplier, because it operates on a relation. This is going to give me another relation. So what I have is the status and the city only, okay? So I have 20 London, 10 Paris, 30 Paris, and 30 Athens. Can anybody tell me why there is one tuple missing in there?
Because they're both the same.
Exactly, because you have to remove the duplicates in doing that, because otherwise the result will not be a relation. So this particular operation projection will remove any duplicates if they arise. Because if you left the duplicates, you would not have a relation, and therefore you wouldn't have disclosure, okay? So you're never going to have any duplicates. Duplicates will be eliminated automatically in the query. So that's why we have less tuples. But other than that, it does not tuple selection. The other thing that I might do is to have the union. Now this is where we need to remember set theory. And for those of you that might be rusty on it, I did have a pen. Yes, I did. So remember that the union, tell me that there is something here that helps to wrap words. Can anybody see anything? Somebody left a phone there, but I guess that's not going to be. Okay, I'm going to try to use this bit only then. So if we have a set A and a set B, the union is going to be all of the elements that are in A and all of the elements that are in B, or both. So it's going to be all of this and that. So it's going to be everything that is either in A or B or both. Okay? That is the union of two sets. Whereas the intersection of two sets, A and B, is going to be the elements that are in both A and B only. So the intersection is where they intersect, like where they both, and the set difference is going to be, if I have A set difference B, is going to be all of the elements that are in A but not in B. So it's going to be everything that is in A but not in B. So this bit is not part of I minus B. Okay? What if I have B minus A? Is that the same? No, because it's going to be everything that is in B but not in A. So it's going to be this B, this bit. That is going to be B minus A. So A minus B in sets is not the same as B minus A. Okay, so having looked at those, we have those in the context of relational algebra. So the union, equally to in sets, is going to be the tuples from, if you have two relations, one is called R and one is called S, the union of R and S is going to be all of the tuples that are in R and in S, so either in R, in S, or in both. So it's every tuple from R and every tuple from S, okay? So if I have something like this, I have R, and I have S1 Smith and S4 Clark, and S, which has S1 Smith and S2 Jones. The union of R and S is going to be every tuple that is in R and or in S. So S1 Smith 20 London is going to be there. S4 Clark 20 London is going to be there. S1 Smith 20 London does not need to be there because it already is. And S2 Jones 10 Paris is also going to be there. So that is going to be the union of R and S. The important thing with the union, the intersection, and the set difference is that they have to be applied to what we call union compatible relations. Now, two relations are union compatible if they have the same attributes drawn from the same domain. So that means that I need to have an S number, an S name, and a status and a city in both in order to be able to compute the union, the intersection, or the set difference. The same attributes drawn from the same domain. So if this relation didn't have a status and city, for example, I could not say R minus S because they don't have the same attributes drawn from the same domain.
But the query, it will be one query, or if we make query, right? If you want to take some data from two tables,
Yes.
or it will be two queries like join.
If we do this, this is one operation, it's the union operation, okay? But the important thing is that in order to apply it, I need to have the same attributes in the first table as in the second. If that's not the case, I could project some attributes from one table and from the other, and once they are union compatible, I can then do R minus S, S minus R, R intersection S, or R union S. But I cannot do it unless they are union compatible. So if I only had S number and S name in R, I would have to project S number and S name in S before I could actually make that union, because they have to be union compatible.
Would null values be applicable?
Yes, they could be there, and you just kind of, you will pick them across as you do, you know, because it will be, providing you don't end up with duplicate data, then you'll be fine. So that is the union. Equally, the intersection is very similar. We have, like we did in the Venn diagrams, where we have the intersection of R and S are going to be the tuples that are appearing both in R and in S. The difference we had before, the middle bit, which was those that were both in one set and in the other. So if I do the intersection R intersection S, then I am going to have S1 Smith 20 London, which is the only one common to both. That will be the intersection. In order to do the intersection, they have to be union compatible, i.e., both relations have to have the same attributes from the same domain. Are we clear on that? Yes. Good. You are illuminated today. You will walk away with so much knowledge. So the set difference is the same as the set difference that we saw. We have R minus S or S minus R. And they are not going to be the same. Because if we think about R minus S, we are talking about all of the tuples that are in R, but not in S. So if I look at all of the tuples that are in R, but not in S, I get S4, Clark, 20, London. What if I wanted to know S minus R? What do I get?
Jones.
Jones, exactly, because that's the only one that is in S, but not in R. Again, to apply that, they have to be union compatible. So we're looking for the same set of attributes drawn from the same domain. So now we go to the Cartesian product. And the Cartesian product we've already looked at when we look at the mathematical kind of definition of the Cartesian product. So with tuples it's the same. What we have with the Cartesian product is that if we have R and S, what we're going to have as a result of the Cartesian product is a concatenation of every tuple in R with every tuple in S. So if I have I tuples and N attributes in R, and J tuples and M attributes in S, I end up with I times J tuples, this multiplied by these tuples, and I also end up with N plus M attributes. So I have here the supplier, and I have the shipment. Now if I do the Cartesian product of the supplier times the shipment, I'm going to have S1 Smith, S1 P1 300, S1 Smith, S2 P2 400, S2 Jones, S1 P1 300, and S2 Jones, S2 P2 400, because I'm concatenating everything from the first relation with everything from the second relation. In this case, they don't have to be union compatible. This applies even if they have different attributes. I'll end up with N plus M attributes and I plus J, I times J tuples. Are we all happy with that? Now, generally speaking, we don't really want to do the Cartesian product because we end up often with tuples that we don't particularly want. So we end up with quite a large number of tuples, and some of the tuples are meaningless. So for example, if I have five suppliers and 6 products, I end up with 30 tuples. Now, what I might want to do instead of that is to do the Cartesian product, R times S, but restrict it to those where the supplier number in the first relation matches the supplier number in the second relation. So normally what I want to do is to restrict the Cartesian product to those where there is a match between one key in one relation and the foreign key in the other relation. In that sense, I will get the suppliers with their shipments only, not anybody else's shipments. So supplier 1 will only concatenate with shipments with supplier 1. Supplier 2 will only concatenate with shipments for supplier 2. Because generally speaking, I don't want to see supplier 1 concatenated with shipments for supplier 2. So what I want to do is this, okay? So I want to say, okay, but I want to have S1 Smith, S1 P1 300, and S2 Jones, S2 P2 400. So I want those where there is a match. So that is a subset of the Cartesian product. And that is how joins on tables are defined. Joins are the main operations that we do when we go on to do SQL. And it's how we join tables together. And we use the primary key foreign key to make that connection between tables. So we implement the relationship like this. So what we do is, the Cartesian product will return on concatenations, which is not useful. So we want to restrict that to a limited subset, which means some predicate. So the predicate could be a zeta join predicate, which is the join of RMS using a predicate which is of the form some key in A in R relation matches some key in the B relation, and the match could be a less than equal to, an equal to, not equal to, greater to. But really, the ones that we most often use is what we call an equijoin, i.e. where the match is an equal match. We could have others, but the ones that we generally use are the equijoins. And those are the ones where we're looking for an equality match between one key and another. And in fact, the natural join is an equijoin over common attributes of R. So we don't have to specify the attribute because we're going to do it over whatever is the common attribute. So in one relationship we had S number, in the other relationship we had S number, so the natural join is going to be defined over the common attribute, which is S number. Okay? So if I talk about a natural join, which is that symbol over there, like a tie, then I have an equijoin, which is the equal, I'm looking for equality over common attributes. So therefore it's going to immediately give me S1 Smith P1 300, S2 Jones P2 400. It's not going to return as I had before. It's not going to return as I did here the S number for R and the S number for S because it knows they are a common attribute, so it only returns 1. Okay, because that is a natural join, defined over the common attribute. So I no longer have to worry about that. And it's only going to be there for one occurrence. Now, the kind of joins that we have been looking at are what they call inner joins. And that means that the results only appear where there is a match. So let's say that I have two tables. One of them I have R with S1, Smith, S9, another and S2. And in the other one I have the shipments for X1, P1, S3, P4, and S2, P2. If I do a natural join of those tables over the common attribute, which is S number, what I'm going to get is any tuple that appears in the first table which finds a match in the second table. But when there is no match, those tuples will not be returned. So I'm going to get S1 Smith, because there is an S1 in this table, and I'm going to get S2 Jones, but I don't get S9 another, because there is no match in the second table. And that's what we call an inner join. If I want to get those where there is no match, which sometimes I do, then I have to have a different types of join. I need an outer join instead of an inner join. And I define an outer join. It could be a left outer join or a right outer join. If I go for a left outer join, which has the tie symbol open in that left, then I want the tuples for R that do not have a matching value in the common attribute in S. So if I do R left outer join S, what I want is S1 Smith is going to appear, S9 another is also going to appear, even though it hasn't got a match in S, because I'm doing a left outer join, and S2 Jones is going to appear. But what won't appear is S3, because that doesn't have a match in this table, but it's not included in a left outer join. If I want that, I need to do a right outer join. Okay? So I'm going to have all of the ones that appear and found a match, and all of those ones that didn't find a match from R to S, because that's a left outer join. If I do the right outer join, then I'm going to get the ones in R that find a match, plus those from S that didn't have a match. So in this case, I will have S3. And note that when there is no match, what I end up with is null values, where there is no match. Okay, so the resulting thing, because S3 doesn't have a match, has a null value, and then S3. Okay, are we all happy with that? The difference between an inner join, an outer join, left or right. And equally, we could have a full outer join, which allows the tuples that don't have a match from R to S or from S to R. So if I want to do a full outer join, then I will say R full outer join S is going to give me all of the tuples that were in R, in S, the ones that were in S and not in R, plus all those where there was a match. So it includes both sets, so everything will be reflected back, with null values where there is no match. An additional join is the semi-join, which is specified as R semi-join S, and that is going to give you the tuples of R which participate in the join of R and S. So it's going to be like an inner join, but they will not return any attributes from S. So it only returns the attributes from the first relation. Okay? And it returns those where there is a match. So if I have something like the staff who work at branch X, what I'm going to have is all the staff details for that branch, but not the branch details. I just have the staff that has that match, but not the branch details. That's the semi-join. So now we're going to look into how we formulate a query. Because the idea here is that what we have to do is we have to learn how to build queries in relational algebra step by step. More complex queries, so not just one thing, but we need to put all these operations together. We need to be able to answer a query by putting together things like joins and intersection and set difference to answer our queries. So it's going to be some kind of like, most queries will require some kind of selection, projection, and join, at least. And they might involve also other things. Natural joins are what we normally use when we're talking about a join, those over the common attribute where there is an equality involved. So let's say that I have a query that says, get supplier names for suppliers who supply at least one red part. Now, when I have to answer that query in relational algebra, or write it in relational algebra, I need the supplier names. They are in the supplier table. Okay? I need to know what color the part is. That information is in the parts table. And I also need to know who supplies what. So I can only link them via the shipment table. So in order to answer that query, I'm going to have to join the tables. I'm going to do some selection, because I only want the red parts. And I'm going to have to do some projection, because I only want the names. So I'm going to build that query together, step by step. So I'm going to do the supplier names, which is going to be projection, who supply at least one red part, which is going to be a form of selection, and I'm going to link all these three tables together. So that's going to require joins. So I'm going to write a relational algebra that is going to do that. So I start by saying, okay, let's first, and there's any number of ways in which I could do this, they will give me the same result. So I could start with doing one thing or another. It doesn't matter which way, providing I get to the right result at the end. So I could start by saying, let me look for the red parts only. So that is the selection. So I'm going to take the parts table, and I'm going to use temporary tables, because every relational algebra operation returns another relation as its result. So I'm going to put it on a temporary table, which I call temp1, a temporary relation, and then I can use that. So I'm going to say temp1 is equal to selecting the color equal red from the parts table. So that answers a little bit of my query, and maybe I only get these three tuples, which correspond to the red only. So I've answered some of my query, but I still need to know more. So what do I need from that? Well, the only information now that I know which the parts are is the part number. I need that to link to the shipment table so that I can find who supplies them. But I don't need the rest of the information. So I could now project from temp1, which has only red parts, the part number, because I don't care about the rest. So I end up with P1, P4, and P6. Are we all happy with that? Yes. So now I need to look at the shipment table, because I need to be able to know who supplies these parts, P1, P4, and P6. So I then say, okay, let me join temp2, which has the P numbers for the red parts, to shipment. That's going to put all the information on shipments of red parts into my result. So I end up knowing that there is S1, who supplies P1, P4, and P6, S2, who supplies P1, and S4, who supplies P4. Okay? I haven't finished answering my query, because I need the name of the suppliers. So I therefore need to move on to the supplier table. But in order to do that, the only thing that I really need is the supplier number, so that I can link to the supplier table. So I can now project S number from temp3, so that I just have S1, S2, and S4. So I now have the supplier numbers, or suppliers who supply red parts. But what I need is the names. So I need to go back to the supplier table to get that information. So then I say, okay, temp5 is going to be equal to temp4, natural join supplier. And that is going to put my S1, S2, and S4 together with the information on suppliers. So I now have all of the information on suppliers who supply red parts. What I need to do is project the name only, because that's the only thing I'm interested on. So I project the name from temp5, and I get Smith, Jones, and Clarks. And that is the result that I was looking for. that answers my query. So I build up that query as a series of steps. So I can do it like that, or so it is perfectly valid for you to do it one step at a time using intermediary tables. Equally, we could use this closure property to stack the operations together into one, if you wanted to, because that will give you the same results. So if I wanted to do it all at once, I will say, okay, the innermost bracket is the one that is going to be executed first. So the first thing that we're doing there is color is equal to red from par, that selection. Having done that, then I project the P number for that result. And then I join that to shipment. I then project the S number from that result, and then I join that to supplier. And then finally, I'll project the S name from that result. So I've done exactly the same thing, but I've done it in shorthand notation instead of one step at a time. Now, if you have to answer an exam question, I don't mind whether you do a shorthand notation or one step at a time. What I care about is that you get the right sequence correctly, the one that is going to deliver the right results. Are we all happy with that? So that is what you need to practice and get to know. So just a note on relational calculus, because we don't study relational calculus, but we have to mention it because it is a non-procedural language, and that means that with relational algebra, we specify how we are going to get to the result. We say, we join this with this, we project this, so we are, at each stage, we're specifying the steps that we need to take our result. Relational calculus is non-procedural. We don't specify how we are going to get the results, we just say what results do we need. Okay, so it's a non-procedural language. So it also operates in tuples and domains. It takes the name from mathematics, from predicate calculus, and the idea, because it's non-procedural, is that we do not have any indication of how we are going to execute the query. We specify what we want. Now, it might look something like that. So for example, if I have a query like list the staff who manages properties for rent in Glasgow, and I want to specify that in relational calculus, I have to write something along the line of there where I have get a staff such that there exists a property for rent where the staff number in P is equal to the staff number in S and the city is equal to Glasgow. So I'm specifying what I want as a result of my query, but now how that query is going to be executed. From that point of view, is non-procedural. Every relational calculus expression has an alternative relational algebra expression and vice versa. So you can go from relational algebra to relational calculus and the other way around. So if we wanted to say that in relational algebra, we'll be saying select the city is equal to Glasgow from the join of the property for rent and the staff. Now in doing this is missing a bracket. In doing that, I'm specifying how that is going to be achieved, because I'm saying I want to join this with this, and then I want to select this. So I'm giving a method for the strategy. So that is why this, the top one, is non-procedural, whereas this one is procedural. So, as I say, they are like equivalent. There are other non-procedural languages that we are going to study, mostly SQL. So because we study SQL, which is non-procedural, we don't get into relational calculus, but you should be aware that it exists, that you always have equivalent expressions to relational algebra. There are also things like query by example that are also non-procedural. But we won't go into details of them. So if I now want you to do this, and we don't have time for this, get what I could do with, that I don't have, is something to get rid of the, does anybody have a tissue that I can use? Failing to have a blackboard, a whiteboard wiper, which happens in these rooms all the time, and is very annoying. Does anybody, nobody has a tissue? No? Nobody, oh, you're so messy, nobody's always going to have a tissue. Fabulous, okay, we're going to do it then, pulling the screen up, because I can't clean that. I'm not doing it with my hand, so. Right, somewhere here. Let's see. What is? It's somewhere, oh yeah, it's not even automatic. I was looking for the, there's no way we're going to get a lot of 4, but hey, that's the best we're going to be able to get. Right, so we'll try to do it there. So we have get part names and colors from parts supplied by suppliers located in London with the status over 10. So if we want to do this in relational algebra, what do we need to do? Can anybody suggest any operations that we have? We need part names and colors, which are in the parts table, for parts supplied by suppliers located in London, where they are located is in the in the supplier table, with the status over 10. So how do we write that query? Suggestions. What do we begin to do? Yeah. So the first thing is that let's look for the suppliers that are located in London with the status over 10. So how do we achieve that with relational algebra? What operation do we need? Restriction or selection, yes. So we need to say select, okay, and our predicate is going to be city equals London, yeah? So those are going to be the ones that are located in London, and we could have and status greater than 10, okay, from the S table. Okay? So if we do that, we will now have only the tuples that are suppliers that are located in London with the status over 10. Now, what else do we do?
Projection of supplier number.
Yeah, all that we need really, because at the end of the day we only need the part numbers. So we don't need much of the information, but we do need the supplier number in order to connect with the other tables. So we could now say, let's call this temp 1. Now I could say temp 2 is going to be equal to project supplier number from temp 1. So now I only have my supplier number. What do I have to do? We don't need the name of the supplier, because at the end of the day we only need part names. Yeah, we need to join with the shipment table, because we need to know what parts the supplier supplies. And we can only do that by joining to the shipment table. So what we need to do now is we need to take temp 3, which is going to be temp 2, which are already the supplier number for the suppliers that have a status over 10 and are in London, and we join them with the shipment table. And in doing that, we now have all of the information on the parts they supply. We have the part number plus the quantity for each of them. So what do we do now?
Projection.
Yeah. We project, at the moment, all we need now is the part number, because what we want to do is we now want to go to the part table and select those that match. So really for that we only need the part number. So we say, okay, let's have temp 4 equal to project the part number from temp 3. Because that's the only information I need at this stage. And I am done? Am I done? No. What do I need to do now? Yes, the names are in the part table, so I need to join to the part table now. So I need to be able to then take this temp 5 becomes temp 4, join parts, the P table. Okay? Now I have all of the information on the parts that are supplied by the specific suppliers which were from London and have a status over 10. Am I done? No, because what do I need? Yeah, because the only thing I'm asked to return is the parts name, so I have to project that and nothing else. And then I do have a result. So I have result is equal to project the name or the part name from temp5. And now I am done.
Don't need the colours as well.
Oh, and the colors, yes, sorry. Not just the name, the color as well. So I have to project those two attributes. And then I'm done. So what about, we don't have time for the second one, yes we do, but we have no board. We'll try over here, even though we might have to write something else. What if I wanted to get the name of suppliers who do not supply any parts, or where the supplier city is London? How do I go about that? Any suggestions? As it gets trickier. You can almost see it like two separate queries. Okay, so think of it initially as two separate queries. The first one says, name of suppliers who do not supply any parts, or where the supplier city is London. Let's start with the suppliers, where the supplier city is London, because that is easy. How do I get that?
That was the first one on that.
Yeah, so basically, if I just had, for the first one, I would have temp1 is equal to select city equals London from the supplier table, okay? Now, what do I really need at the end of that? Name. So, I need to project the name, because that's the only information I need. So I could say, okay, now my temp2 is equal to project name from temp1. So I got one set of results that I need. I need another set of results, which are the suppliers who do not supply any parts. So how do I know those that do not supply any parts? Exactly. They will be, if they supply something, they will be in the shipment table. If they don't supply anything, they won't be in the shipment table. So how do I get all of the suppliers, but not those that are in the shipment table? Could be, or set difference. Set difference will do it, because we're going to have all of the suppliers minus the suppliers that are in the shipment table. And then we have the suppliers that don't supply anything. So I could then have my temp3 will be equal to the suppliers minus, I want all of the suppliers that are not in the shipment table. So in fact, let me just do project S number from the supplier table, and that's one set. And then I want to have temp4, which is project S number from the shipment table, okay? And now all I have to do is temp5 is equal to, remember that they have to be compatible, so I need to subtract something that is the same in terms of the attributes. So I can therefore say temp3, which are the supplier number only for all of the suppliers, minus temp4, which is the supplier number from those that appear in the supplier table. So the result of that is going to give me the suppliers that are not supplying anything. And to put the final thing together, I got one set of results, okay, which are, in fact, to be a little bit, no, I'm still going to have to go back. Now I need to get the name of those suppliers. Because what I need to do is eventually to put together these results with the others. Okay, so I need to get the name of the suppliers. So I have to go back to the supplier table to find the names for those. So I need to then, join temp5 with the supplier table to get back all of the details that I don't have of the suppliers. And then I want to project only the supplier name Are we all happy with that? So now I have the name of the suppliers who are supplying new parts in one hand here in temp 7, and here I have the name of the suppliers who are located in London. So I can put them together with what? Union. Exactly. So I can say my result then becomes temp 2 union temp 7. And then I have just the names of those that meet the first part of the query or the second part of the query. Okay? Good. Now you can go to your seminars.